A nuclear power plant is a thermal power station in which the heat source is a nuclear reactor. As is typical in all conventional thermal power stations, the heat is used to generate steam, which drives a steam turbine connected to an electric generator which produces electricity. As of the 23rd of April 2014, the IAEA report there are 435 nuclear power reactors in operation, operating in 31 countries. Nuclear power stations are usually considered to be baseload stations, since fuel is a small part of the cost of production. Their operations and maintenance and fuel costs are, along with hydropower stations, at the low end of the spectrum and make them suitable as baseload power supplies. The cost of spent fuel management, however, is somewhat uncertain. History. For more history, see nuclear reactor, nuclear power and nuclear fission. Electricity was generated by a nuclear reactor for the first time ever on September 3, 1948 at the Extant Graphite Reactor in Oak Ridge, Tennessee in the United States, and was the first nuclear power station to power a light bulb. The second, larger experiment occurred on December 20, 1951 at the EBRI Experimental Station near Arco, Idaho in the United States. On June 27, 1954, the world's first nuclear power station to generate electricity for a power grid started operations at the Soviet city of Obninsk. The world's first full-scale power station, called a Hall in England, opened on October 17, 1956. Systems. This section has recently been translated from the German Wikipedia. The conversion to electrical energy takes place indirectly, as in conventional thermal power stations. The fission in a nuclear reactor heats the reactor coolant. The coolant may be water, a gas, or even liquid metal depending on the type of reactor. The reactor coolant then goes to a steam generator and heats water to produce steam. The pressurized steam is then usually fed to a multi-stage steam turbine. After the steam turbine has expanded and partially condensed the steam, the remaining vapor is condensed in a condenser. The condenser is a heat exchanger which is connected to a secondary side such as a river or a cooling tower. The water is then pumped back into the steam generator and the cycle begins again. The water-steam cycle corresponds to the Rankine cycle. Nuclear reactors. The nuclear reactor is the heart of the station. In its central part, the reactor core's heat is generated by controlled nuclear fission. With this heat, a coolant is heated as it is pumped through the reactor and thereby removes the energy from the reactor. Heat from nuclear fission is used to raise steam, which runs through turbines, which in turn powers the electrical generators. Nuclear reactors usually rely on uranium to fuel the chain reaction. Uranium is a very heavy metal that is abundant on Earth and is found in seawater as well as most rocks. Naturally occurring uranium is found in two different isotopes, uranium-238, accounting for 99.3% and uranium-235 accounting for about 0.7%. Isotopes are atoms of the same element with a different number of neutrons. Thus, U-238 has 146 neutrons and U-235 has 143 neutrons. Different isotopes have different behaviors. For instance, U-235 is fissile, which means that it is easily split and gives off a lot of energy, making it ideal for nuclear energy. On the other hand, U-238 does not have that property despite it being the same element. Different isotopes also have different half-lives. A half-life is the amount of time it takes for half of a sample of a radioactive element to decay. U-238 has a longer half-life than U-235, so it takes longer to decay over time. Since nuclear fission creates radioactivity, the reactor core is surrounded by a protective shield. This containment absorbs radiation and prevents radioactive material from being released into the environment. In addition, many reactors are equipped with a dome of concrete to protect the reactor against both internal casualties and external impacts. Steam turbine. The purpose of the steam turbine is to convert the heat contained in steam into mechanical energy. The engine house with the steam turbine is usually structurally separated from the main reactor building. It is so aligned to prevent debris from the destruction of a turbine in operation from flying towards the reactor. In the case of a pressurized water reactor, the steam turbine is separated from the nuclear system to detect a leak in the steam generator and thus the passage of radioactive water at an early stage. An activity meter is mounted to track the outlet steam of the steam generator. In contrast, boiling water reactors pass radioactive water through the steam turbine, so the turbine is kept as part of the radiologically controlled area of the nuclear power station. The generator converts kinetic energy supplied by the turbine into electrical energy. Low-pole AC synchronous generators of high-rated power are used. Cooling system. A cooling system removes heat from the reactor core and transports it to another area of the station, where the thermal energy can be harnessed to produce electricity or to do other useful work. Typically, the hot coolant is used as a heat source for a boiler, and to pressurize steam from the drives one or more steam turbine-driven electrical generators. Safety valves. In the event of an emergency, safety valves can be used to prevent pipes from bursting or the reactor from exploding. The valves are designed so that they can derive all of the supplied flow rates with little increase in pressure. In the case of the BWR, the steam is directed into the suppression chamber and condenses there. The chambers on a heat exchanger are connected to the intermediate cooling circuit. Feed water pump. The water level in the steam generator and nuclear reactor is controlled using the feed water system. The feed water pump has the task of taking the water from the condensate system, increasing the pressure and forcing it into either the steam generators or directly into the reactor. Emergency power supply. Most nuclear stations require two distinct sources of off-site power feeding station service transformers that is efficiently separated in the station's switchyard and can receive power from multiple transmission lines. In addition, in some nuclear stations the turbine generator can power the station's house loads while the station is online via station service. Transformers which tap power from the generator output bus bars before they reach the step-up transformer. Even with the redundancy of two power sources, total loss of off-site power is still possible. Nuclear power stations are equipped with emergency power. Workers in a nuclear power station. Nuclear engineers, reactor operators, health physicists, emergency response team personnel, Nuclear Regulatory Commission resident inspectors. In the United States and Canada, workers except for management, professional and security personnel are likely to be members of either the International Brotherhood of Electrical Workers or the Utility Workers Union of America, or one of the various trades and labor unions representing machinists, laborers, boilermakers, millwrights, iron workers, etc. Economics. The economics of new nuclear power stations is a controversial subject, and multi-billion-dollar investments ride on the choice of an energy source. Nuclear power stations typically have high capital costs but low direct fuel costs, with the costs of fuel extraction, processing, use and spent fuel storage internalized costs. Therefore, comparison with other power generation methods is strongly dependent on assumptions about construction timescales and capital financing for nuclear stations. Cost estimates take into account station decommissioning and nuclear waste storage or recycling costs in the United States due to the Price-Anderson Act, with the prospect that all spent nuclear fuel, nuclear waste, could potentially be recycled by using future reactors. Generation IV reactors are being designed to completely close the nuclear fuel cycle. Presently, however, there has not yet been any actual bulk recycling of waste from ANPP, and on-site temporary storage is still being used at almost all plant sites due to waste repository construction problems. Only Finland has stable repository plans. Therefore, from a worldwide perspective, long-term waste storage costs are uncertain. On the other hand, construction or capital cost aside, measures to mitigate global warming such as a carbon tax or carbon emissions trading increasingly favor the economics of nuclear power. Further efficiencies are hoped to be achieved through more advanced reactor designs. Generation 3 reactors promise to be at least 17% more fuel efficient and have lower capital costs, while futuristic Generation IV reactors promise 10,000 to 30,000% greater fuel efficiency and the elimination of nuclear waste. In Eastern Europe, a number of long-established projects are struggling to find finance, notably Berlin in Bulgaria and the additional reactors at Cernavodă in Romania, and some potential backers have pulled out. Where cheap gas is available and its future supply relatively secure, this also poses a major problem for nuclear projects. Analysis of the economics of nuclear power must take into account who bears the risks of future uncertainties. To date, all operating nuclear power stations were developed by state-owned or regulated utility monopolies, where many of the risks associated with construction costs, operating performance, fuel price, and other factors were borne by consumers rather than suppliers. Many countries have now liberalized the electricity market where these risks, and the risk of cheaper competitors emerging before capital costs are recovered, are borne by station suppliers and operators rather than consumers, which leads to a significantly different evaluation of the economics of new nuclear power stations. Following the 2011 Fukushima nuclear accidents, costs are likely to go up for currently operating and new nuclear power stations, due to increased requirements for on-site spent fuel management and elevated design basis threats. However, many designs, such as the currently under construction AP1000, use passive nuclear safety cooling systems, unlike those of Fukushima which required active cooling systems. This largely eliminates the necessity to spend more on redundant backup safety equipment. Safety and accidents. In his book, Normal Accidents, Charles Perrow says that multiple and unexpected failures are built into society's complex and tightly coupled nuclear reactor systems. Such accidents are unavoidable and cannot be designed around. An interdisciplinary team from MIT has estimated that given the expected growth of nuclear power from 2005 to 2055, at least 4 serious nuclear accidents would be expected in that period. However, the MIT study does not take into account improvements in safety since 1970. To date, there have been 5 serious accidents in the world since 1970, corresponding to the beginning of the operation of Generation 2 reactors. This leads to on average 1 serious accident happening every 8 years worldwide. The nuclear power plants cannot explode like a nuclear bomb because the fuel for uranium reactors is not enriched enough, and nuclear weapons require precision explosives to force fuel into a small enough volume to go supercritical. Most reactors require continuous cooling to prevent a core meltdown, which has occurred on a few occasions through accident or natural disaster, releasing radiation and making the surrounding area uninhabitable. Plants must be defended against theft of nuclear material and attack by enemy military planes or missiles, or planes hijacked by terrorists. Controversy. The nuclear power debate is about the controversy which has surrounded the deployment and use of nuclear fission reactors to generate electricity from nuclear fuel for civilian purposes. The debate about nuclear power peaked during the 1970s and 1980s, when it reached an intensity unprecedented in the history of technology. Controversies. In some countries, proponents argue that nuclear power is a sustainable energy source which reduces carbon emissions and can increase energy security if its use supplants a dependence on imported fuels. Proponents advance the notion that nuclear power produces virtually no air pollution, in contrast to the chief viable alternative of fossil fuel. Proponents also believe that nuclear power is the only viable course to achieve energy independence for most Western countries. They emphasize that the risks of storing waste are small and can be further reduced by using the latest technology in newer reactors, and the operational safety record in the Western world is excellent when compared to the other major kinds of power plants. Opponents say that nuclear power poses many threats to people and the environment. These threats include health risks and environmental damage from uranium mining, processing and transport, the risk of nuclear weapons proliferation or sabotage, and the unsolved problem of radioactive nuclear waste. The environment issue is also regarding discharge of hot water into the sea. The hot water modifies the environmental conditions from the marine flora-fauna. They also contend that reactors themselves are enormously complex machines where many things can undergo wrong, and there have been many serious nuclear accidents. Critics do not believe that these risks can be reduced through new technology. They argue that when all the energy-intensive stages of the nuclear fuel chain are considered, from uranium mining to nuclear decommissioning, nuclear power is not a low-carbon electricity source. Reprocessing. Nuclear reprocessing technology was developed to chemically separate and recover fissionable plutonium from irradiated nuclear fuel. Reprocessing serves multiple purposes whose relative importance has changed over time. Originally, reprocessing was used solely to extract plutonium for producing nuclear weapons. With the commercialization of nuclear power, the reprocessed plutonium was recycled back into MOX nuclear fuel for thermal reactors. The reprocessed uranium, which constitutes the bulk of the spent fuel material, can in principle also be reused as fuel, but that is only economic when uranium prices are high and disposal is expensive. Finally, the breeder reactor can employ not only the recycled plutonium and uranium in spent fuel, but all the actinides, closing the nuclear fuel cycle and potentially multiplying the energy extracted from natural uranium by more than 60 times. Nuclear reprocessing reduces the volume of high-level waste, but by itself does not reduce radioactivity or heat generation and therefore does not eliminate the need for a geological waste repository. Reprocessing has been politically controversial because of the potential to contribute to nuclear proliferation, the potential vulnerability to nuclear terrorism, the political challenges of repository siting, and because of its high cost compared to the once-through a fuel cycle. In the United States, the Obama administration stepped back from President Bush's plans for commercial-scale reprocessing and reverted to a program focused on reprocessing-related scientific research, accident indemnification. The Vienna Convention on Civil Liability for Nuclear Damage puts in place an international framework for nuclear liability. However, states with a majority of the world's nuclear power stations, including the U.S., Russia, China and Japan, are not party to international nuclear liability conventions. In the U.S., insurance for nuclear radiological incidents is covered by the Price-Anderson Nuclear Industries Indemnity Act. Under the energy policy of the United Kingdom through its Nuclear Installations Act of 1965, liability is governed for nuclear damage for which a UK nuclear licensee is responsible. The Act requires compensation to be paid for damage up to a limit of £150 million by the liable operator for 10 years after the incident. Between 10 and 30 years afterwards, the government meets this obligation. The government is also liable for additional limited cross-border liability under international conventions. Decommissioning. Nuclear decommissioning is the dismantling of a nuclear power station and decontamination of the site to a state no longer requiring protection from radiation for the general public. The main difference from the dismantling of other power stations is the presence of radioactive material that requires special precautions to remove and safely relocate to a waste repository. Warranty period of operation of nuclear power stations is 30 years. One of the wear factors is the deterioration of the reactor's shell under the action of neutron bombardment. Generally speaking, nuclear stations were designed for a life of about 30 years. Newer stations are designed for a 40 to 60-year operating life. Decommissioning involves many administrative and technical actions. It includes all cleanup of radioactivity and progressive demolition of the station. Once a facility is decommissioned, there should no longer be any danger of a radioactive accident to any persons visiting it. After a facility has been completely decommissioned, it is released from regulatory control, and the licensee of the station no longer has responsibility for its nuclear safety. Historic accidents. The nuclear industry says that new technology and oversight have made nuclear station much safer, but 57 small accidents have occurred since the Chernobyl disaster in 1986 until 2008. Two-thirds of these mishaps occurred in the U.S. The French Atomic Energy Agency has concluded that technical innovation cannot eliminate the risk of human errors in nuclear station operation. According to Benjamin Sovacool, an interdisciplinary team from MIT in 2003 estimated that given the expected growth of nuclear power from 2005 to 2055, at least 4 serious nuclear accidents would be expected in that period. However, the MIT study does not take into account improvements in safety since 1970. Flexibility of nuclear power stations. Nuclear stations are used primarily for baseload because of economic considerations. The fuel cost of operations for a nuclear station is smaller than the fuel cost for operation of coal or gas plants. There is no cost saving if you run a nuclear station at less than full capacity. However, nuclear stations are routinely used in load-following mode on a large scale in France. Although it is generally accepted that this is not an ideal economic situation for nuclear stations. Quote, unit at the German Bibli nuclear power plant is designed to decrease its output 15% per minute between 40 and 100% of its nominal power. Boiling water reactors normally have load-following capability implemented by varying the recirculation water flow. Future power stations. A new generation of designs for nuclear power stations, known as the Generation IV reactors, are the subject of active research. Many of these new designs specifically attempt to make fission reactors cleaner, safer and/or less of a risk to the proliferation of nuclear weapons. Passively safe stations are available to be built, and other reactors that are designed to be nearly foolproof are being pursued. Fusion reactors, which are still in the early stages of development, diminish or eliminate some of the risks associated with nuclear fission. Two 1600 MWE European pressurized reactors are being built in Europe, and two are being built in China. The reactors are a joint effort of French Avda and German Siemens AG, and will be the largest reactors in the world. One EPR is in Olkiluoto, Finland, as part of the Olkiluoto nuclear power plant. The reactor was originally scheduled to go online in 2009, but has been repeatedly delayed, and as of September 2014 has been pushed back to 2018. Preparatory work for the EPR at the Flamanville nuclear power plant in Flamanville, Manche, France was started in 2006, with a scheduled completion date of 2012. The French reactor has also been delayed, and was projected, in 2013, to launch in 2016. The two Chinese EPRs are part of the Taishan nuclear power plant in Taishan, Guangdong. The Taishan reactors were scheduled to go online in 2014 and 2015, but that has been delayed to 2017. As of March 2007, there are 7 nuclear power stations under construction in India, and 5 in China. In November 2011, Gulf Power stated that by the end of 2012, it hopes to finish buying off 4,000 acres of land north of Pensacola, Florida in order to build a possible nuclear power station. In 2010, Russia launched a floating nuclear power station. The £100 million vessel, the academic Lomonosov, is the first of 7 stations that will bring vital energy resources to remote Russian regions. By 2025, Southeast Asia nations would have a total of 29 nuclear power stations. Indonesia will have 4 nuclear power stations, Malaysia 4, Thailand 5 and Vietnam 16 from nothing at all in 2011. In 2013, China had 32 nuclear reactors under construction, the highest number in the world. Expansion at 2 nuclear power stations in the United States, Vogtle and V.C. Summer Nuclear Power Station, located in Georgia and South Carolina, respectively, are scheduled to be completed between 2016 and 2019. The 2 new Vogtle reactors, and the 2 new reactors at Virgil C. Summer Nuclear Station, represent the first nuclear power construction projects in the United States since the 3 Mile Island nuclear accident in 1979. Several countries have begun thorium-based nuclear power programs. Thorium is 4 times more abundant within nature than uranium. Over 60% of thorium's or monazite is found in 5 countries: Australia, the United States, India, Brazil, and Norway. These thorium resources are enough to power current energy needs for thousands of years. The thorium fuel cycle is able to generate nuclear energy with a lower output of radiotoxic waste than the uranium fuel cycle.